physicsforme.com presents Newton's law of universal gravitation in the 5-minute video series which explains selected physics concepts in only 5 minutes. Newton's law of universal gravitation states that any two bodies exert a force on each other that is proportional to the product of their masses and inversely proportional to the square of their distance apart. The constant of proportionality is known as the gravitational constant g, and its value can be determined experimentally. It is called a universal constant because it has the same value irrespective of the properties of the interacting bodies. Used together with Newton's second law of motion, F equals ma, Newton's law of universal gravitation enables the calculation of the trajectories of bodies under gravitational forces, including the orbits of planets around the Sun. To understand Newton's law of universal gravitation and its implications, let us simulate the motion of two masses under their mutual gravitational forces. The ratio of the two masses shown here can be varied using this slider. Now the mass ratio is 1, so that the two bodies have the same mass. And now the ratio of the two masses is 100. The yellow arrows denote the gravitational forces exerted by each body on the other. Note that they are always equal and opposite, even when the masses are different, in accordance with Newton's third law of motion. The forces act along the line joining the centers of the two masses. Let us change the ratio of the masses back to 1. Once we click the Start button, the two masses will start moving under the influence of their mutual gravitational forces given by Newton's law of universal gravitation. They will move because Newton's second law of motion, F equals ma, implies that if you have a resultant force F acting on a body of mass m, then it produces an acceleration given by F over m. Let us see this in action now. As you can see, the two bodies are starting to move. The green arrows denote their velocities. The white marks indicate their positions after successive equal intervals of time. The fact that the marks become more widely spaced demonstrates that the two bodies accelerate. Note that the acceleration is not constant because the force increases as the two bodies get closer, in accordance with the inverse square law of gravitation. Let us now change the mass ratio to 50 and restart the simulation. Although both bodies experience the same force, the one with smaller mass experiences a much larger acceleration and therefore moves faster than the larger one. As an example, an apple falling from a tree due to the force of gravity of the Earth also pulls Earth with the same force, but because the mass of Earth is so much larger than that of the apple, Earth moves a negligible distance compared to the distance through which the apple falls. Let us now look at the application of Newton's law of universal gravitation to planetary orbits. This simulation calculates the orbit of a planet approximately the size of Earth around the Sun. For simplicity, the motion of the Sun is neglected. This is justified because the mass of the Sun is more than 330,000 times that of Earth. As you can see, the orbit of the planet around the Sun is elliptical. Different shapes of elliptical orbits are possible by changing the initial speed and angle of the planet. For example, Changing the speed to 35 gives a more elongated ellipse. And if we change the angle to 50 degrees, it gives an orbit that looks like that of a comet. All these orbits are calculated using Newton's law of gravitation together with Newton's second law of motion, F equals ma. This illustrates the predictive power of Newton's law of universal gravitation. We hope you have found this video useful. For more videos and other free learning and teaching resources in physics, please visit us at physicsforme.com.